All right, so we're going to do the practice exercises here. In exercises 1 through 10, determine whether each relation is a function. Give the domain and range for each function. The most common way that this is taught, just because it's easy, is to look for repetitions in the x value. So what a lot of people do is they just remember that it's x comma y, and then let's say x1 comma y1, and then you have x2 comma y2. Basically, if these numbers were like 4 comma 6 and 4 comma 8, you would say the relation is not a function, because the same input value 4 maps on to two output values, 6 and 8. And that's not allowed. So not a function. Okay. In other words, y, these outputs are not functions of x, because if you stick that number in 4, you need to have one output. Because if you think about it on a graph, if you've got 4 plotted right here, and let's see, 2, 4, 6, 8. And you're going to say, well, I put in 4 and I get out 6. So you're going to go over here to 6, line it up with the 4, put a dot. And then you say, well, I put in 4 and I get out 8. Go over here, put a dot. If you connect those dots and draw a line, you have a vertical line. And that fails everywhere. If you took the square root of 4, if we didn't define the square root of a number for functions to only be positive, it should be plus or minus the square root of 4. So if you had f of x equals plus or minus, if that was there, and you weren't told in advance not to consider only positive values, and you put in f of x equals the square root of x, and then I said, okay, let's plug in 4, f of 4 equals plus or minus the square root of 4, then you would tell me the square root of 4 is 2, so it's plus or minus 2. And we'll get into this later, but you actually have two solutions. You have x1 and x2. So we're going to get rid of this function notation. We're going to say y equals x1 and y equals x2, which is equal to 2 and then negative 2. All right? What does that look like? Well, we could play with this a little bit more, and I could show you how I'm going to come up with this, but if you'll just trust me, if I plotted this, it would have a point there at 0, 0, and then it has a point here at 4, 2, and a point here at 4, negative 2. And so it forms what looks like a quadratic parabola tilted over 90 degrees to the right. See? Watch. Looks like a quadratic equation. In fact, it is. I mean, if I said f of x equals x squared, I'm trying to show you the relationship between square root and squared. And I plugged in f of 2 equals 2 squared. See, I took my solutions. This is solution 1. Plug it back in over here. I would say, well, I put in 2, so I'm going to go right 2. That's 2. And then 2 squared is 4. So I'm going to go up 4. There's my point. F of 0 equals 0 squared. Well, that's just 0. There's where that origin dot comes from. And then you can use the symmetric reflective property here and say, well, look, I have this, it's a mirror graph, right? So I'll just mirror it. You don't really have to plug in the other numbers. You already know it's going to be symmetric about the axis of symmetry. That's what that's called, the axis of symmetry. And so if you went over 2 to the right and up 4, then you're going to go back to 0, 0, go over 2 to the left and up 4. And then you can draw it. I just drew a function. That's x squared. For sure. Y equals x squared. Bingo. Works. It doesn't violate the vertical line test anywhere. But that assumes that this axis right here is the y-axis and this axis is the x-axis. But what we're talking about is a question where it's like this, where that's the y-axis and this is the x-axis. So you see the problem? Now I have a problem that violates the vertical line test absolutely everywhere, including at 0, 0, because there are 2 solutions. x1 equals 0, x2 equals 0. Okay? It's called a double root. The fundamental theorem of algebra says that if it's x squared, there's going to be 2 answers. If anybody tells you otherwise, just tell them they're an idiot. Look at everywhere I'm violating the vertical line test, every single place, because I haven't restricted my square root function to ignore the negatives. But let's just say that I did, and that instead of plotting what I just plotted, I plotted this. The only positive solution I had was 2. Okay, the square root of 4 is 2 if we're only considering the positive. 1, 2. Skip 2, 3, okay. And then 1, 2, 3, 4. Okay. So I stuck in 4 and I got back 2. So I go over to 4. If you're just starting out with this, I often tell people, go over to 4 and take a ruler and draw a vertical line with the pencil. Now, that was 4 input. What was the output? It was 2. Go over to 2, make a horizontal, and then where they intersect, that's the point. If you don't know, if you're just getting started, that might help you. That right there is the point 4, comma 2. And I want to be sure to fill it in because an open circle like that actually means it's not defined at that point. Okay, now remember, try taking the square root of 0. Okay, it's 0. So you have, x1 equals 0, x2 equals 0. Technically speaking, a double root. But we're only taking the one value. So we'll go here, down here. Okay? Now, if you understand how these curves work, you could just kind of interpolate, but you could also plug in these middle numbers. And if you took the square root of 2, you would get 1.41414 like that. So it's kind of like you go over to 2, and then 1.414, what is this? It's halfway between, that would be right here, maybe, like that. Good enough. You know what the square root of 3 is. If this is 1.4 and that's 2, then it's between 1.4 and 2. Well, what's between 1.4 and 2? We got 1.75, 1.65 maybe. So if this was 1.5, maybe you could go here and like this. You can kind of interpolate the point, and then you can kind of see what it wants you to do. The square root of 1 is 1. And now it makes it easier to connect the dots. I always connect the dots by shading. So, because I don't, it's hard to make a drawing of a quadratic or a square root. So I'm gonna, on my pencil's laying flat, see, I'm gonna shade it in until I get kind of a feel for that curve before I go with anything like definitive. And now I have kind of a guide path to follow with my permanent marker, and you're just connecting the dots. Kind of like that. Arrowhead up top. Turn it back. Remember your axes. This is y or f of x. And this is x. This is the independent variable. This is the dependent variable. Domain deals with the independent variables. So what independent variables can this take? Well, it can take in 0. Can it take in -1? No, because the square root of -1 is I, and we're only considering real solutions. I would love to plot I, but I'm not going to do that right now. The square root of -2, well, that would be 2I. See? So it can't take negatives, but it appears, since I put this arrow here, that this is going to go to infinity. It'll take any positive number. It doesn't have to be a whole number or a number that can be reduced to a fraction. It can take anything. Okay? And so what you want to do to write your, I don't know, the professors have different way of writing domain and range. So the domain can be written like this. You can literally write out all the, you can say the domain is, as an inequality, 0 okay, less than or equal to, this is inequality notation. Less than or equal to x, less than or equal to infinity. Okay, that's one way of writing it. You could also write it using set notation, where it's got to be x is, oh, look, read x from this way, like your eyeball is over here looking this way. X is greater than or equal to 0. Okay, so you have a compound inequality here, so you can write greater than or equal to 0. You use this bracket and you say 0, comma, infinity, and then infinity always takes the parenthetical closure. And now again, read this. X is always less than or equal to infinity. Okay, so infinity is greater than or equal to x. So does this make sense? This right here? That's way 2. This is also the domain. Okay. The final way is set builder notation. Okay, and what you would do there is say the set, these curly braces, the set of all x such that x can take the following values, and then basically you're going to put in one of these two things. You could say 0 dot 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 infinity. Okay, that's one way of putting it. Or you could put this in there, 0 comma infinity, and kind of combine the two like that. Another symbol you could use if you wanted to do this a little bit differently is you could say x is in that's this symbol here. X is somewhere between 0 and infinity. That means right there, that symbol means in. Or is an element of the set of. I mean, I don't know what the professor wants there, so I'm going to stop the video there. So that was the introduction video to show you what is really going on under the hood. I hope this was of some benefit, because we can start flying through the problems. I don't mind, using the check the x's if they repeat. It's not a function. But if you didn't see this, you might not understand why. And that was, knowing why that we don't draw this, why we draw this. It's the same thing. And then I thought you would think it was cool that basically there's a relationship between, it's like a 90-degree rotation. Or if you want to think about it in another way, if this is where you start and then you're going to rotate this thing counterclockwise, how many times you have to rotate it? 90 degrees, 180 degrees, 270 degrees. So it would have to rotate around when we get into trigonometry, I'll explain what I'm talking about. But you're rotating counterclockwise 270 degrees around to get to that. Anyway, don't worry about that for now. Please make sure to like, subscribe, comment, and hit that notification bell so you're always updated when we get new videos posted. Thank you very much.